Hey guys, my name is João Gilberti, I'm from Brazil, and today I'm turning 16 years old, and for this very special day, I'm going to solve with you guys a very special problem. IMO Shortlist 2021 Problem C1, Combinatorics. This problem is one of the best Math Olympiad problems I've ever seen. If you want to try it, go ahead and then watch this video. Don't waste such a good problem. So this is the spoilers alert, and now let's go to the statement of the problem. Given an infinite set S of positive integers such that there are 4 integers in S with different GCD, such that call them A, B, C, and D, such that the GCD of A and B is different from the GCD of C and D. The problem wants us to prove that there are 3 numbers x, y, and z on the set such that GCD of xy equals GCD of xz, which is different from the GCD of y and z. So this is a very simple problem, and here's some background on how I found this problem and why do I find it so interesting. The story behind me and this problem is the following. I was in the IMO Brazil training, and they gave this problem as problem one of the mock tests for the IMO we did. And I tried this problem a lot, and I thought, this sounds like a well-known fact. It shouldn't be on shortlist. And after thinking about the problem for a while, I had an idea, and here goes the spoiler. What if I created a graph to map the numbers and their GCDs and connect things when their GCDs are equal, or paint some edges? And I thought about some graphs that I could do, and I thought it was crazy at a moment because I didn't know how to solve the problem and how to use this graph. And when I was getting out of the mock test, I saw 2 of my friends discussing the test. And when they said that they solved the test with graph theory, I was so happy. I couldn't explain it because I had this idea and I thought I was crazy because I thought that this idea would make no sense. So when my friends told me they solved it with graph theory, I got so happy. And the solution I'll present you is from one of my friends whose name is Mateus, and his solution is very brilliant. So let's go for it. Actually, in the test, the graph I taught was the dual graph of Mateus, which I will talk to you later about. But the idea in Mateus' graph is to paint the edges, which is pretty much more natural than painting the vertices, which was my case, what I should have tried to do. But here's the graph, and here's how to solve the problem, and here's how Mateus, my friend, solved this problem. The idea of the problem is actually thinking about the simplest graph you can make. So consider the following graph. The vertices of this graph are the numbers on S, so it's an infinite graph, and you color the edge between them with their GCD color. So it's a complete graph, and you color it with their GCD. So suppose, for the sake of contradiction, that there is no triple x, y, and z in S satisfying what the problem asks. Notice that in terms of the graph G, what we want to prove is that there exists a triangle in the graph on the form that is appearing on the screen, with 2 edges of the same color and 1 edge of different color, because then we would have 2 equal GCDs and a third different GCD. Let G be this graph that I talked about. The first claim that we should make, which I was able to do during the test, is G has an infinite monochromatic clique. Monochromatic clique is a configuration where all the vertices are connected and all the edges that connect the vertices have the same color. The proof is quite simple. Consider a fixed number A in S and another number B on S. So consider all the possible values of GCD of A and B as B varies through the infinitely many elements of S. But now notice that as GCD of A and B can vary only through the divisors of A, as the GCD has to divide A, as B varies and B can take infinitely many values, there is at least a GCD that repeats infinitely many times. Let T be this GCD that repeats infinitely many times when you take GCD of A and B, with B being an element of S. And let D and E be two numbers on S such that the GCD of A and D equals the GCD of A and E, which equals T. So here's what we're going to do. If the GCD of D and E is different from T, we have the triple that we wanted, as the GCD of A and D equals the GCD of A and E, which is different from the GCD of D and E. So we have to suppose that for every D and E that generates this GCD that appears infinitely many times, the GCD of D and E equals the GCD of A and D, which is T. This means that in terms of the graph G, we have an infinite monochromatic clique, because if you pick A and pick every number that makes the GCD of A and this number equal to T, we have that we can color the edge between A and this number with a color T. And as we have infinitely many numbers, and if we pick two of these numbers, we have to connect them with edge of color T. Otherwise, we would have the triple that we suppose that we don't have. We have an infinitely many positive integers in S as we want that generates a GCD of A and these integers equal to T. Hence, there is a monochromatic clique, an infinite monochromatic clique. The second and final claim of the problem is that there is a positive integer in S which is outside of this clique. Suppose, for the sake of contradiction, that this is false. That is, every positive integer in S is on the clique. Then we would have an absurd, because if that were true, every positive integer in S would have the GCD equal to T, which is a contradiction. Hence, we have proved that there is an integer or an element of S and an element of the graph that is outside of the clique. Let this element be D. Notice that on the clique, we have a element V, which when connected to D has an edge with color different than T. Because if there weren't the case, we would have that every element of D, every element of the clique as when connected with D would have the color T, which would mean that D is on the monochromatic clique, which is a contradiction because of the definition of D. Let this different color be R, and let V be the vertex of the clique that connected to D has an edge of color R. Okay, so now we split the problem in two cases. First case is when we have an element, call it W, of the clique that connected to D has color T. Notice that the triple W, V, and D would do the work, because we would have three elements of S which have two of them having the same GCD. That is, the GCD of W and D equals the GCD of W and V, as W and V are on the clique, and this GCD, their GCD equals T. But this GCD is different from the GCD of D and V, which is R. So we will have a contradiction because we supposed that there are no triples of this form. Suppose now that for every edge connecting D to an element of the clique, its color is different from T, because if it is equal to T, we go back to the other case. For the second case, connect D to every element of the infinite monochromatic clique. Then notice that as there are infinitely many numbers on this monochromatic clique, when D is connected to every element, every vertex of the monochromatic clique, and D has finitely many divisors, there is at least a color C that will repeat itself two times. And notice that by the supposition that we made about the colors of the edges from D, we have that the color C is different from T, because we are supposing that there's no color T going out from D to an element of the clique. Let this color C edges connect D to two elements Y and Z of the monochromatic clique. Because Y and Z have color C, we can pick the triple D, Y, and Z, which will satisfy our problem. Because DY has color C, DZ has color C, and YZ has color T, as Y and Z by supposition were on the clique. So then we have finished our problem. because for as we supposed, C is different from T. QED. If you like the video, don't forget to subscribe the channel and give this video a like. Thank you guys for watching, and that's it. Good night.